unveiling a 90-year-old enigma in quantum physics, scientists have made a groundbreaking discovery that could revolutionize the world of measurement. Prepare to be amazed as we delve into this fascinating story. Have you ever wondered why a plucked guitar string eventually falls silent, or why a swing slowly comes to a halt? Physicists have an answer for these everyday observations, calling them damped harmonic oscillators. But when we zoom in to the atomic level, the rules change dramatically. Enter Dennis Clougherty, a professor at the University of Vermont, and his student Nam Dinh. They dared to ask, can atomic systems exhibit similar vibrations to everyday objects? And if so, can we develop a quantum theory to explain it? In a groundbreaking study published in 2025, Clougherty and Dinh presented an exact solution to this puzzle. They cracked the code for a damped quantum harmonic oscillator, a quantum-scale version of a guitar string's motion. But here's where it gets controversial. For nearly a century, theorists have struggled to describe these damped harmonic systems using quantum physics. The challenge? Preserving Heisenberg's uncertainty principle, a cornerstone of quantum physics. This principle states that we can't precisely know both the position and momentum of a particle simultaneously. At the atomic scale, the more we know about one property, the less we can know about the other. The model that Clougherty and Dinh tackled was originally developed by British physicist Horace Lamb in 1900, long before quantum physics was even a thing. Lamb wanted to understand how a vibrating particle in a solid could lose energy. Using Newton's laws, he showed that the particle's motion creates elastic waves that feed back, causing the particle to dampen over time. In classical physics, it's clear that objects lose energy due to friction and air resistance, Dinh explains. But in the quantum world, it's not so obvious. With support from the National Science Foundation and NASA, Clougherty and Dinh reformulated Lamb's model for the quantum realm. To preserve the uncertainty principle, we had to consider the atom's interaction with all the other atoms in the solid, Clougherty says. It's a complex, many-body problem. So how did they solve it? Get ready for some mind-bending science. Through a multimode Bogoliubov transformation, we diagonalized the system's Hamiltonian, which allowed us to determine its properties, they explain. This led to a state called a multimode squeezed vacuum. In simpler terms, the UVM researchers mathematically reformulated Lamb's system, enabling them to precisely describe an atom's oscillating behavior. And this is the part most people miss. Accurately locating an atom's position could lead to the world's tiniest measuring device. The UVM scientists' work predicts how the uncertainty in an atom's position changes with its interaction with other atoms. By reducing this uncertainty, we can measure position beyond the standard quantum limit. In physics, there are ultimate limits, like the speed of light, and Heisenberg's uncertainty principle prevents perfect measurement. But certain quantum tricks can reduce this uncertainty. In this case, by calculating the particle's behavior in a squeezed vacuum state, the noise of quantum randomness in one variable, location, is reduced, while it's increased in another, momentum. This mathematical approach was key to the development of the first successful gravitational wave detectors, which can measure changes in distance 1,000 times smaller than an atom's nucleus. Who knows what other secrets the Vermont theorists' discovery will unlock? Reference: Quantum Lamb Model by Dennis P. Clougherty and Nam H. Dinh. 7 July 2025. Physical Review Research. Funding U.S. National Science Foundation. NASA Headquarters. Join the SciTech Daily newsletter to stay updated on the latest breakthroughs.